Welcome to comp452 computer architecture, and this is lecture 7b. So in this lecture we are going to continue our discussion of MIPS exceptions that we started in the previous lecture. Exceptions continued. Exceptions continued. So in the previous lecture we identified that we will be needing a few signals in addition to the ones that we already have, and we said that we need to flush the instructions or stop the execution of instructions as soon as arithmetic overflow is detected in the EX stage. And we said we already have IF flush signal. This is already present in our design, but we will introduce ID flush for the ID stage instruction and EX flush for the execution stage instructions. And we also said that we will extend program counter mux, which loads a new value in the program counter, because when exception is detected, microprocessor stores the address of the offending instruction in EPC, exception program counter. It also records the cause of the exception in cause register and then jumps to that specific address where operating system gets control. And so these are the new signals we need. New signals, and we need two new registers. One is called exception program counter and the other is called cause register. Okay, so these are the things that we need. And we also said that exceptions are just treated like control hazards. Okay, so today we will see how all these signals are incorporated in our design data path and controller, pipeline data path and pipeline control. And for that purpose, let's load a figure which will this is the figure. Let's see if it's too big yeah, it's too big. I would like to fit it on one page. Yeah, now I can fit it. Now it is, I can see the whole figure on one page. Okay, now this is actually figure 4.66 of text. Alright, Now see, this is the signal that we already have. What does the signal do? If you remember, it sets opcode to 0. All 6 bits are set to 0. Okay, now look, here we have that ID flush, and here we have EX flush. Alright, now let's see all these 3 signals, IF flush, first one, ID flush, second one, and EX flush, the third one. They're all coming from the main controller. Okay, they're all coming from the main controller. Now these are the original 10 signals. Here we have the original 10 signals that we studied in the beginning while we were designing the control for our pipe single cycle. While we were studying the single cycle control design or controller design of the single cycle MIPS processor, we identified these 10 signals. So these 3 signals are in addition to those 10 signals. And now see, we have an OR gate here. What does this do? It ORs a signal coming out of the hazard detection unit and going into the OR gate, and the other signal is ID flush, which is coming out of the control signal and going into the other input of the OR gate. Now this signal which is coming out of the hazard detection unit, if you remember, this signal is asserted when load instruction is followed by an instruction that uses the register written by the load word. Okay, so basically it inserts a bubble in load use hazard case. We saw this in data hazards. Okay, so now we have ID flush. So this ID flush, what it's going to do is it's going to set all the 10 control signals to 0, all the 10 control signals to 0, and because of that, the instruction in the ID stage, it will become a no-op. It will become a no-op. Okay, now let's look at this EX flush signal. This EX flush signal. This number 3, EX flush signal. EX flush signal is also coming out of the controller, and here you see it is going into 2 different muxes. This is the mux which deals with the signals intended for write back stage, and this mux, it deals with the signals, control signals, which are intended for the MEM stage of the pipeline. So we have separated these 2 muxes here, and both of these muxes have a single control input, which is EX.flush signal. So whenever this signal is asserted, you can easily see that 0 will be propagated to the output of the mux, which means that the instruction in the EX stage will not have any effect on memory or registers. In other words, the instruction in the EX stage will not write any register in the register file, and it will also not write the data memory. This is what happens when we set all the control signals to 0. And look, this is where we are setting the control signals of memory stage to 0, and this is where we are setting the control signals of the write back stage to 0. Okay, now let's come to the third the other important thing. Look, this is the signal. Look, this was the program counter plus 4 value which was propagating from the IFID pipeline register all the way to this IDEX pipeline register. So when it exits from the IDEX pipeline register, this value gets stored in exception program counter. You can see here EPC exception program counter, and the processor also stores the cause of exception in this cause register. Now keep this thing in mind that EPC gets the address of the instruction which immediately follows the exception calling instruction. EPC gets the address of PC plus 4. So if so whenever the as soon as the operating system gets control, it must subtract 4 from the value in EPC to get to the correct instruction. This is what it has to do, because we are storing PC plus 4 in the, look, this is 4 and this is current program counter value. So PC plus 4 is propagated and it is stored in exception program counter. And the last thing is this mux. Look, this mux had only 2 inputs, but now it has 3 inputs, and this is the third input. This is the address where the microprocessor will jump to which the microprocessor will jump, and operating system gets control. So operating system gets control, and then operating system does whatever is necessary to handle that exception. Now this mux, the control lines or the select lines of this mux are not shown, which doesn't make any difference because we know every mux has a set of control lines, one or more control lines. So this is the whole architecture with exception handling built in. Exception handling has been added to our pipelined data path and control. Okay, so now let us consider an example, and after that we will be nearly done, and let's take a look at this example. So we have this instruction sequence. Let's write it here. Here we have addresses, and here we have instructions, and here we have operands. Okay, and all the addresses are in hex. So let's say at address 40 we have subtract register 11, register 2, register 4. Then on the next address, at the next address we have AND instruction. We have 12, 2 and 5. On the next, at the next address we have OR instruction 13 to 6, and next address has add instruction, which is 1 to 1, and then at address 50 we have SLT 15 6 7, and at 54 we have a load word and 16 50 and 7. Now this is the instruction sequence that we are given, and when we invoke the when exception occurs in add instruction, let's say exception occurs in add instructions. So when this exception is handled, the processor jumps to address 0 hex 8000 0180, and here we have this instruction. This is just an example. 1000 and 0, and at the very next address we have another stored word. You can look up this register number 26 and 27. What are their names? So we have to show what happens when exception occurs in the add instruction, this instruction. Now this add instruction will go from fetch stage to decode stage and then to EX stage, and in EX stage when ALU performs addition, let's suppose that it detects an overflow, arithmetic overflow. Now what is the processor going to do? So first thing the processor will do is save the address of the following instruction, PC plus 4, and this is PC plus 4, 4C plus 4 is 5. So 50 is stored in exception program counter. Now the question is, in which clock cycle will this happen? Okay, in the first clock cycle, this instruction goes into fetch. In the second one, this goes into fetch. In the third clock cycle, this goes into fetch. In the fourth clock cycle, this one goes into fetch. So in the fifth clock cycle, this add instruction goes to decode, and in the sixth it goes to EX. So in sixth clock cycle, sixth clock cycle. the sixth clock cycle is the earliest where we can detect exception in this code, assuming that detection exception is arithmetic overflow exception. Basically, none of these has anything to do with arithmetic overflow. These are, oh, actually, by the way, I'm sorry, subtraction can have an overflow, but and or do not have any arithmetic overflow as a result of their execution, because these are not arithmetic instructions, these are logical. These are not arithmetic operations, these are logical operations. So in the sixth clock cycle, it is arithmetic overflow is detected, and EPC is filled with 50 hex, which is the address of the SLT instruction, this SLT instruction. Alright, so let's take a look at clock cycle 6. What will be the state of the pipeline in clock cycle 6? Let's take a look. So here let's make it 80. Yeah, this is good. Now see, this is the add instruction which we are assuming will cause an arithmetic overflow, and this is clock cycle 6. Clock 6. In clock 6, this instruction, add instruction, will reach the EX stage. Now see, it is followed by SLT, and this instruction is the one which follows SLT. Let's go back and take a look. Yeah, this LW, it comes after SLT. Now when we detect exception, we store program EPC, we fill EPC with 50. You can see 50 here. We also store the proper cause. I don't know, I think it's either 10 or 12, I forgot. 10 or 12, one of them is for undefined instruction and the other one is for overflow, arithmetic overflow. We talked about it last time in lecture 7a. So cause register is written, EPC is written, and then this EX flush signal will be activated as soon as this exception is detected. It will cause this 0 and this 0 to propagate to the output of these two muxes, and further execution of add instruction, further execution of this instruction will be stopped, because when control signals all become 0, nothing will be written in the write back stage, nothing will be written in this write back stage, because a reg write signal will be 0, so nothing will be written. And since this is an add instruction, it has nothing to do with data memory, but data memory, memory read and memory write signal will also be set to 0. Okay, what next? We have to disable or flush this SLT and this load word. So what we do is we use this ID flush signal and we insert a 0 in all control lines. Okay, so SLT will be turned into no op bubble. Okay, and then we also assert this ID flush signal if flush signal, if dot flush signal. This is going to make the opcode in this register, pipeline register, to all 6 zeros. 6-bit opcode will be set to all zeros, and this instruction will also be converted into no op, and then it's going to load this value. It's going to load this value into the program counter. This value is 8000-0180. This is the value. It is going to be loaded into the program counter, and the instruction for data memory will be pulled up. Look. Now this 0x8000-0180 is going into the program counter. It has gone into the program counter. Look, see here. And now what's going to happen is that the instruction, this instruction will be oh, I'm sorry, what did I do? What was I trying to do? Yeah, this is what I was trying to do. I was trying to show you that now this instruction is going to be fetched from instruction memory, this one, and it is going to be executed. So look, SW26,000, $1,000. So this is the new instruction which is being fetched now. Alright, so this is how we implement exceptions in our pipelined processor. Now this bubble will leave the pipeline in the next clock cycle. After that this bubble will leave, then this bubble will leave, and then the pipeline will be filled with instructions from exception handler or instructions of exception handler. And after handling the exceptions, it is up to the operating system to decide whether to kill the program or to restart the instruction, or whatever is the policy, it will be followed. Alright, so this completes our discussion of exceptions. Actually, let me tell you, the discussion is completed partially, because in chapter 5 we will have more exceptions to handle, and we will talk about them once we start chapter 5. So for now we are done with our discussion of exception for the time being, because when IO requests arrive, that's also an exception. And similarly, there are, when page fault happens, it's an exception. When TLB miss happens, that's an exception. So there are a number of exceptions which we will talk about in chapter 5. Now, it is important that hardware and software, which means microprocessor and the operating system, they act in conjunction to handle the exceptions. So now, what is the duty of hardware. What is the duty of hardware? Let's write it down here. I want blank. I want A4. Okay. So let's see. Duty of processor. Duty of processor. Number 1, record instruction address in EPC, the instruction that caused exception. 2, record cause of exception in cause register. 3, stop execution of exception causing instruction immediately midstream. 4, let all prior instructions complete. 5, flush all following instructions. And finally, load a predefined address in program counter. Or in other words, transfer control to operating system. Okay, these are the duties of the processor. Okay, now what are the duties of OS? Duty of OS, operating system. 1, examine the cause register. Examine cause register. Based on the value in cause register, take steps to handle exception. Okay, take steps to handle exception. So, and either after handling exception, this is happening. Either kill the program or uh, or restart it. Either kill the program or restart it. Now we will see that when TLB miss happens, when TLB miss exception is detected, or when page fault exception is detected, or when disk IO request arrives and it is detected, then these are the cases in which after handling the exception, the process is not killed but it is rescheduled. And we will talk about this in chapter 5. But if it's in arithmetic overflow or it's a hardware fault, then program is killed. Normally kills the program. OS normally kills the program. We will talk about the memory related exceptions in the next chapter, and we will talk about the page faults and TLBs in detail. So now what I want you to do is to once again reading assignment. Section 4.9, 5.1, 5.2 and 5.3 of textbook. Okay, so this is the chapter on memory. And this is the section on exceptions. Okay, so this is where we are going to stop. By the way, there is a check yourself quiz. Please try to answer the check yourself quiz on page 332 of the textbook. Okay, and also read, there are a couple of elaborations. I'll not talk about those elaborations, but I can ask questions related to what is said in those elaborations. So make sure you read it. You read them. There are 2 or 3 elaborations. Okay, so this is where we are stopping, and our next lecture, in our next lecture, we will start discussing the memory organization. All right, so let's stop, and there we go.